Part A, find g at -3, find g prime of x, and evaluate g prime at -3. So for this, I've already written out g of x, and I drew a quick sketch of what f of t looks like. So for this, for the first part, find g at -3, we're just going to plug -3 right into this function, which will give us 2 times -3 plus the integral from 0 to -3 f of t dt. So for this part right here, this is the same. You can rewrite this as negative integral from -3 to 0 f of t dt. And the reason why is when you flip it, you're rotating these two, you tack a negative on there. So now you have -6 minus the integral from -3 to 0 f of t dt. So now I'm integrating from -3 to 0 of f of t, which is this region, which nicely is right under the circle, or quarter of the circle, that they told us about earlier in the problem. So because this is a circle, we can use pi r squared, but because it's a quarter, we're going to need to quarter that. Plugging in 3 because it's our radius, we're going to get 9 pi over 4, so that's minus carries over, and bring down our -6, and that is g at -3. Next is finding g prime of x. So for this, we're just going to be taking the derivative of g of x, so derivative of 2x, just 2, plus the derivative of this. So this comes out as f of x. Let's make that a better parenthesis. F of x. Now, the reason being that if you were to integrate this and then take the derivative, this integrated first will be f of x minus f of 0. And these are capitalized, showing that this has been integrated. Then you would take the derivative of this, because it's asking for the derivative, you would get f of x minus this cancels, thus leaving just f of x. So this is g prime of x. And then finally, evaluating g prime of -3 using this function, carry down our 2 plus f at -3, which is 0. So 2 plus 0, 2. That's our final answer for g prime at -3. Part B. Determine the x-coordinate of the point at which g has an absolute maximum on the interval -4 less than or equal to x, x less than or equal to 3. Justify your answer. So first part, we need to find the absolute maximum. So to do this, we're going to need to take the first derivative of g of x, which is g prime of x equals 2 plus f of x. We solve for this in the other problem in the first part. Then we need to solve for the 0, which will give us a potential point. So plug in 0 here. 0 equals 2 plus f of x, which leaves us with f of x equals -2. So now, looking at my little redone graph, we're trying to find when this line, somewhere on this line, we get -2. Now it's going to be the y value. So, looking here, we look down here, -1, -2, draw a little line across to this point right here, which lines up at x equals 2.5 or 5 over 2. So x equals 5 over 2 is a potential value for the maximum on G. So now we have to justify the answer, and what determines a maximum is when the derivative goes from increasing to decreasing, thus leaving you with a maximum point here. So we need to prove that on the interval -4 less than or equal to x, less than, not, it doesn't have to be equal to, hold on. Less than 5 over 2, this has to be increasing. Is that right? Yes. And then this has to be decreasing. So, going back to our graph, we will find that because you have a first value at 2 plus f of x, 5 over 2 will give you -2, and as you decrease in value, this value will increase. So meaning at x equals 1.5, you're going to get 0, which is 2, thus positive. So that is true. And 5 over 2 for all this. So as you get larger, plugging in x equals 3 into f of x, you're going to get a value of -3, which makes this value negative. So then that means that that's negative. That justifies the answer. Part C. Find all values of x on the interval -4 less than x, x less than 3, for which the graph of G has a point of inflection. Give a reason for your answer. So for this one, basically for inflection points, we just need to find where the second derivative, G prime prime of x, equals 0. So looking back, we knew that G prime of x is equal to 2 plus f of x. So the derivative of this is G prime of x equals f prime of x. So looking back at our graph, which looks 1, 2, 3, 1, 2, 3, 1, 2, 3, which looks something like this. Ta-da! We're looking for when the derivative of the graph goes to 0. There's only one point that does that, at x equals 0, right there. And the reason being is that on this side, increasing, 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 decreasing, decreasing, which means that there is a change in sign. And that is what we're looking for. That means that the answer is x equals 0. Part D. Find the average rate of change of f on the interval -4 less than or equal to x, x less than or equal to 3. There is no point C, -4 less than C, C less than 3, for which f prime of C is equal to that average rate of change. Explain why this statement does not contradict the mean value theorem. Alright, so for this, we need to find the average rate of change. So doing that first, we're going to have f of 3 minus f at negative 4 all over 3 minus negative 4. Plugging in the values, f at 3 is negative 3, f at negative 4, put f there, f at negative 4 is negative 1, so minus negative 1 is just plus 1, all over 3, 2 negatives, so 3 plus 4, 7, which equals negative 2 over 7. Now for the second part of this statement they make, and why does it not contradict the mean value theorem? So what this is, in total, it does not contradict the mean value theorem because the mean value theorem states that it has to be differentiable on all these points between negative 4 and 3 for the point C and f prime of C to exist and whatnot. So in total, again, the mean value theorem requires that everything be differentiable from negative 4 to 3, but in this case, at the point x equals negative 3 and x equals 0, the graph becomes undefined.